Hello guys! Today I want to talk about the electrical and mechanical equivalent between physics and electronics. There is an electrical and mechanical equivalent, and as you can imagine, one of these elements is the spring, the mechanical spring, which is obedient to the Hooke law minus k times x, and the capacitor. But why is that? And why the system, as you can imagine, the mass with the spring is basically equal to an LC circuit. So why is that? Let's see. So the capacitor, first let's do a bit of electronics. So the capacitor obeys to the equation I equal to C times dV over dt, meaning that the capacitor is a device that has zero current when there is constant voltage, and this is true. Now, the inductor instead obeys to the equation V equal to L times di over dt. This means that if the current goes suddenly to zero, the voltage will be much higher. You will have spikes. The inductance is responsible for spikes, and the capacitor keeps the voltage stable. You can have endless interpretation of these two devices. And the resistor obeys to the Ohm law, V equal to R times I. Now, let's see what happens in the mechanical domain. In the mechanical domain, we have a spring, we have the mass, and we have the damper. Now, to understand why these are equivalent, we first have to understand the concept of voltage and force. So why the voltage can be approximately seen as a force? Why is that? Well, if you did an exam called mechatronics simulation, it would be more clear. But the reason is simple. When you write the first Newton law, the mass, which is F equal to m times A, which is equal to m times dV over dt, it resembles the equation of the inductor. So, V is F, L is m, and di over dt is dV over dt. So basically, there is a concept of, in the circuit, the voltage source, and the voltage source is the force, and the current that is flowing to the circuit, the flux, is the velocity. Now, there is a long and very boring explanation to why actually it's like that. And to make it work like that, you have to actually have some consideration. I will show you why also in a physics software. But let's continue now with the spring. The spring obeys to the Hooke law, which is F equal to K times X, the module of course. Now, I have F and I have I, so we have to do a little bit of trick. We can use the mechanical way, or you can use the electronics way. It's the same. Let's use the electronics way. So we have the V, which is equal to 1 over C times dt I dt. Now, if we do the integrals on both sides, we will have that V is equal to 1 over C times the integral of I times dt, which is Q. So basically, Q is the movement And if I divide this by the time, I obtain the current, which is, if the Q are the charges that I need to store inside the capacitor, if I study the Q over the T, I'm studying basically the flux, okay? I'm studying the current. So everything comes around. And here you have the equivalent. V equal F, this is the factor K, and Q is X. And also the energy stored by a capacitor is 1 over 2 CV square, and this is E equal to 1 over 2 1/2 K X square. Yeah, naturally you have to write this in the other form which has the charge, but it's always Q square anyway. The damper now and the resistor have the same equation, because the force of the damper is minus beta times the X over the T, okay, which is minus beta times V. So now now that we have discovered that they are basically the same equation, let's make these two circuits. So in the first case, I will produce LRC, and I will apply a step force. And in the other environment, I will have my mass M1 attached to a spring. This mass is infinite, to M2. We will plot in this case we will plot the voltage, and in this case we will plot the movement, the displacement, or whatever. So let's bring this guy. And also another thing. Since this holds true, now you can treat the problem, and I can show you also this one. You can treat the problem of the three masses put together. Now let's suppose that this is in an ideal condition. I apply a force F. I have M1, M2, and M3. If I say that the acceleration A is shared by everyone among the system, and it obeys, of course, in an ideal condition, Newton law. So F equal to M times A. A is equal to the applied force F over the sum of M. If I wanted to find the contact forces, I could use the same concept as a voltage divider, meaning that the problem is equivalent to this one. I have a voltage source and I have three inductances in series. With a bit of patience, you will discover that the force F is actually partitioned between the masses. If all the masses are equal and all the conditions are the same, you should find that, it's a bit more complicated, but yes, you should find that at this point you have like a partition, exactly like you have here. But we will see also this on the software. So now first let's open, no, I don't care. So now let's open first Analysis Spice, and let's use the classical voltage between 0 and 1 volt, just because it's easier. 1 nano, 1 nano, on to I don't care. And let's put a resistor of 1 milli, an inductor of 10 nano, and a capacitor of 1 nano. 1 nano, 1 nano, 1 milli. Now we have to assume that actually, of course, the capacitor is not charged, so we will call this node A, and we assume that dot IC of VA is equal to 0, so that we have actually to charge the capacitor. And now we can run the simulation for 100 nanoseconds. Should be enough. Now, if I check the voltage A, you see that it is pretty oscillating like an LC circuit. That's because my damping, which is the resistor, is very low. Now, if I increase the resistor, so I increase the damping factor, this will decrease pretty fast, I say. So, what's the meaning of this? I am applying a force, I am applying a voltage, and the system is oscillating. In absence of friction, which is, for instance, 1 milli, this will oscillate almost indefinitely. Almost. Because it's not true anyway. If I put, for instance, 1 millisecond, you will see that eventually comes to 0. That's because Spice has some resistor anyway. You cannot eliminate complete resistor in Spice. Even if this was 0, you will still have some resistance anyway. Because this has some resistance, this has some resistance, so you will have it anyway. But now we can take this. So let's make more realistic and let's put 1 milli. Let's reduce to 10 micro. And now you will have it. Your oscillation. Yeah, there are some models, some equations that you already know from physics classes. Now let's open this beautiful software. And now let's play with some magical blocks. So let's open the grid because I want to make this very precise. And yes, let's realize this little block. So now I'm putting a mass, which, okay, I have to make the forces visible first. So now as you can see, there is the mg force and the normal force. Naturally, this plane is supposed to be infinite, and naturally it is the idealistic plane. You can play whatever you can play with this software in whatever you want, and but now we will focus to the equivalent mechanics. So we can also show the components. You can see I can apply a force. You see, and we can also show the values of this. So now we have 0, 0 dot Newton. I don't like it. Let's recreate the mass a little bit. I think a little bit higher. Okay, like this. That's better. You can even liquefy it, but we don't care now. Okay, so let's pick a material, mass, friction. So what we want to take into account in this simulation is the material of the mass, of the test mass, because we have to create another mass which basically will be our wall. Ooh, wrong. Again, wrong. So this is the wall, the mass M2, okay? And we will make this mass exactly like an ideal wall. To do so, you have to click on fixate. So this mass cannot move, and it is basically our wall. So now if I try to apply a force, let's apply a force to this guy. Let's run the simulation. As soon as I apply a big force, boom, it will just bounce like any wall. Oh, sorry, come back. Like any wall would do. Okay, but we want this to make a bit more precise, so we want to also to control the velocity. So that, as you can see now, I can only move the velocity of my block in the x direction. Don't know how it's surpassed, by the way. So we have to reduce the force a bit because okay, it was set to infinite. Now it should. Okay, so now the force is a little bit limited. It surpassed it anyway, but so visualize the forces. So this is our box. We don't care about this box. So we care about this box instead. Now, as you can see, there is the friction, there is the velocity of x, there is the speed, there is everything that we can find. So if I put another block here, you will discover that, you know, physics works. So as long as I move this block, he will be moving like me. Okay, boom, boom, boom. But we don't care about this guy, so erase it. Now we have to attach a spring because what we want to see is the LC circuit. So we attach the spring here to here. Now if I move it, you see that there is the spring. Naturally, I can move the spring in any direction, but we want to make this exactly like a lattice spice. So we need to be careful. Now let's call the spring Fk, torque, friction, yes, Fr, the air, let's call it Fa1, this is the air buoyancy, and attraction, axle, we don't care about normal components, honestly. Air friction, let's call the Fa2, chain chi no, thruster no, controller no. We can, okay, so we have a bit of friction. Okay, so if I move now, you can see that there is the classic harmonic. This is the classical harmonic plot that we can study. Now we can actually play with it just by right click on it, and we can also make some plots because we want actually to know the beautiful curve that appeared on lattice spice. What we want to reproduce is something like that, okay, because we want to prove that the circuit is the same. So now, where is the resistor? The resistor is basically the friction of the simulation. There is friction here, as you can see. There is the friction here, and also inside the spring, which we can control, put it here, there is the damping of the spring constant, and the target length. So now on the x-axis, I don't want to put the speed, actually, I want to put the position, because that's what we care about. So let's put the position of the x direction, and we want to make the first test. So now let's stop the simulation. Everything has stopped. If I apply a force of the Newton are infinite, so let's reduce to 100 Newton. We can also print the force, and we also want to see the there's few forces, the total force. Okay, we also want to see the total force. As you can see, I can apply also the force in other direction, and it will be immediately, and the components will be immediately available. But we want to make this very, very realistic. So as I'm applying an horizontal force, the friction will take action, and also the Fk, which is the Hooke law, will also take action. So we now perform the simulation by imposing the target length a bit higher to the right, like this. Now, as you can see, nothing has happened because the friction was actually too high. So you can reduce it, and let's see. Yeah, as you can totally see, we have to reduce a little bit the damping to make the same simulation as a lattice spice. So the friction now is set to the minimum. You cannot set it to 0 because if you set to 0, it will start to vibrate. So let's set to 0.1 and the damping also to 0.1. Now, let's pull the spring. We can even do something better. We can increase the spring constant by a lot. And now you can, as you can see, I have the exact same simulation as Analysis Spice. So as you can see, without friction, almost without any friction, I have this ongoing oscillation for how much seconds? Whoa, for 300 seconds almost. I can still reduce the air. I can still put the damping to 0, friction to 0, and let's try this again. Now, without any kind of friction, I create a perfectly stable environment, a perfect oscillation that will not damp in any situation. As you can see, the oscillation is not the rating, which means that this environment is perfectly ideal. But as soon as I increase the friction, you see that the oscillation is decreasing and the movement is about to stop. Now I put to 0 again and will keep stable. So now you can see also the meaning of the spring constant. If the spring constant is higher, also the energy stored is higher. So will be the energy, so will be the force, so will be everything. K is everything into a spring. I detached the gravity, and as you can see, my block is going around for no reason. But this is not realistic. At least gravity at least has to be present. So now I apply the force, as you can see, it's not stopping, but so as you can see, we have simulated the fact that the LCR circuit is equal to the mass, spring, and damper. And the damper is, of course, the friction of the air. Naturally, if you increase these values on the spice, also the frequency of the oscillation, the entity of the oscillation itself will change. It's just, you know, basic equations. You have to increase to 1 second to see the end of this oscillation. So it's just escalated in time. Now we can actually go deeper into the detail of each component. And especially I want to go into detail of the mass and the inductor. Now I told you before that the inductor is the inductor gets very angry if you have a very hideous or very steep change into the current. So how is this true? Let's suppose that we have always a pulse between 0 and a pulse between 0. Yeah, this was correct. 0 and 1. Rise time 1 nano. 1, 1, and 2. Now we put a resistor, like 1 milli. This will generate the current. And this is an inductor. So the T on is just 1 micro. And yeah, that's it. Just 1 micro. This is just 1 nano, which can be a parasitic inductance. We call this A. And dot IC I of L1 equal to 0. And let's see what happens. Now, we expect actually to be 0 because this is a ground, basically, but it's not 0. Because what is happening? Sorry, it's better to it's better to do the opposite. It's a bit harder to interpret. It's better to do the opposite. Yeah, definitely. Okay, so now you can see it. Not much about the inductor voltage, which is the same as before, but the current in the circuit. So now, as you can see, the current has a spike, a huge spike. Negative, but we don't care. The current has these huge spikes. Why is that? Because you're actually making the inductor angry because there is a very, very steep variation in the voltage. So let's reduce this guy to a micro. Should be enough to see it. Naturally, also this will depend on the damping factor that you have, but in absence of resistance, like I'm putting right now, you will have a very, very, very huge spike. This will happen also in power electronic circuit when you have, for instance, the common source inductance, CSI. This inductance, it's true, it's like 1 nano, 2 nano, or also here parasitic inductance of the gate. These are very, very common, but it will cause a lot of ringing, a lot of spikes, which can be troublesome. So you want to dump these guys with resistor R in the gate. Now, coming back to the mechanics, what happens to the mass? Well, it's the same. So this equation says that F can be very huge if there is a big variation of velocity in a small period of time. Meaning that if you apply, for instance, 100 meter per second in a very big velocity in a small time, hence a very big acceleration, the force will be huge. As you can imagine, this is pretty intuitive, but if I create a block of mass m1 and I create another block of mass m2 and I put the velocity, now we can close these boxes. Okay. I can put the box here and I can plot the force that is receiving. So let's plot on the y-axis the magnitude of the force. Now I'm gonna bump with all my force of the mouse inside this mass, and I'm pretty positive that you'll see here a huge force. So let's see. 3, 2, 1, go. Boom. As you can see, my mass has gone away. I don't know where exactly. We're going to go back around. But as you can see, the force was very huge. I'm giving a very huge acceleration. Whoa. Okay, there's the bar, this bug here. Okay. We can just apply the X forces if you want, but the concept remains the same. 3, 2, 1, go. Boom. Oh, it just it just went beyond. So 3, 2, 1, go. Boom. As you can see, there is a huge force that he received. Now it's way clearer. And actually, oh sorry. And actually, we can even do this better. So we can only plot the force of this, but we can also plot the displacement. The acceleration, we can plot it. Yes. No, it's better not the acceleration, but it's better to plot the velocity, the speed. Okay. So that we can see how much variation the speed that we have over time, and we can also plot the I want to make, you could make more plots in one graph, but I want to make them separate. Okay, I wanted to plot also the position x. Okay, so again, let's do this again. And to make things more interesting, I will also modify the material of this, making it to gold. So it has a very big mass. But I want also to make my guy into steel. So now I have more quantity. I have more m times v. Now let's clear out the graphs. 1, 2, 3, 4. And let's do it. 3, 2, 1, go. Boom. Ah. Stop. So now we can really see something. So I applied an external force. I apply an external velocity, that, as we can imagine. And this is the variation of the velocity. Oh, this is really interesting. This is the velocity that he has seen externally, 5 meters per second, and this is the force that he has received as a response, which is pretty high. Considering that his mass is 10 Newton, his gravity force is 10 Newton, he received a force about 110 times his mass. So it is something. And with this kind of force, he actually did 7 meters. Oh, that's nice. So that gives you an idea of what a beautiful punch can do. Well, guys, today I had a lot of fun, and maybe I will do other videos like this in the future. Thank you for following me, and see you in the next video. Bye bye.